Well, today we're going to talk about section chapter 3 in the NTIC book. This first section of this deals with something called linear Diophantine equations. Crazy sounding name, right? Linear Diophantine equations are named after a person, Diophantus, who was a mathematician, lived in Alexandria. Actually, he's Greek, but he lived in Egypt because at that time the Greeks had sort of expanded out into covering a lot of the world, a lot of the world around the Mediterranean at that point anyway. So Diophantus lived in, spelled it wrong. Lived in Alexandria. So people typically got their names with of wherever they lived. Diophantus of Alexandria was how he'd be referred. His dates of birth and death are surprising because they say he lived from about 200, what we now say CE, Common Era, to 284. And the reason for this, the funny business here is we're not really sure when he was born exactly, but we think we know at least that he lived exactly 84 years. So, this is an estimate, but given this estimate, that's supposedly precise. He did a major work that was known as Arithmetica, and unfortunately about half of it is lost. It was in 7 or 8 volumes in the first, I have a, let's see. Okay, so it was 13 volumes, excuse me, but 6 of them have survived in various forms, and the remaining 7 are lost. The famous female mathematician, also at Alexandria, Hypatia, actually studied Diophantus's work and wrote commentaries on it. So there have been a Arabic translation of books that somebody discovered and said, wait, this might be Diophantus's work, but I think the consensus is that was a translation of some of this commentary from Hypatia. Not something you really need to know. I want to tell you why this 84 is there. It's because in another book there's a puzzle about Diophantus, and I'll read it to you first, and then we'll try to keep track of it. It says, his boyhood lasted 1/6 of his life. He married after 1/7 more. His beard grew after 1/12 more, and his son was born 5 years later. The son lived to half his father's age, and the father died 4 years after the son. That's a lot of stuff to keep track of. So let's call X his lifespan. Here's the points it gives us from starting to, from age 0 or birth. He gets to 1/6 of his life is his boyhood. So X over 6 is his boyhood in here. It then says, where is it? He married after 1/7 more. So if we add in X over 7 to that, this is where he was married. So where is that point? Well, you have to add X over 6 and X over 7, and what do you have to do? Find a common denominator and fix these two things so that they have that same, they both have 42 as the denominator. So we have 7x plus 6x. Oh, that's 13x over 42. That's when he got married. Then his beard grew after 1/12 more. I don't know what the heck that, 1/12 of his life in addition, one x over 12 more from there is when he gets a beard finally, which seems a little odd to me. Usually, I think boyhood is the point where, or the end of boyhood is when you begin sexual maturation, and you would have a beard around then, or at least something, peach fuzz. But they have him getting married and even spend some more time before he gets his beard. Maybe he's a late bloomer. His son is born 5 years later, so this is just a +5. And that's when his son is born. The son lives half his father's age, and the father dies 4 years after the son. So here's the son dying, and then D dies himself. And this is 4 years in between. All right, kind of crowding to the end of the board here, but that's the span. So how long is this total span given the data we know? The part I didn't say is that this range from when the son was born to when he dies is half of the total. So we're saying the whole thing is x. I got x over 2 just in there. I'm sorry, it's shrunk. You pretend that there's a dots in the number line right in here. I probably should have planned that a little better. Anyway, if you tally all this stuff up, we need to add one more thing into the fractions. We have 13x over 42 plus x over 12. That'll get me all the way to this point where the beard is grown. And I think I need another common denominator. There's already a 6 in here, so it's what I need is 12 does not go evenly into that, but if I double this side and times this side by 7, top and bottom, we get the same number in the bottom. It's 84. And let's see, it's 26 plus 7, 33 x over 84. So, not mentioned in this puzzle, but a key part of it is all these years are supposed to be integers. Those are whole number dates. So the easiest thing to check is, well, maybe 84, since it's the denominator of this fraction, maybe 84 is what x is equal to. And that would mean this point right here is 33 years old. Running out of ink, sorry. Okay, better get a new one. Now let's see if we can make all this work out. If x is indeed 84, he's got 33 years at this point. How old is he when his son is born? He'd be 38. If we're saying his lifespan is 84, this x over 2 part is 42. 38 and 42 means, I'm trying to add, oh yeah, 80. He's 80 years old when his son dies, and then he dies 4 years later at age 84. It's possible that it could be a multiple of that. So he could have died at age 168, but I think that seems unlikely. Right, so you get to a solution by thinking about this. These fractions and all this stuff is actually dealing with whole numbers, and that's what Diophantine equations are really about. In fact, this is an example of a Diophantine problem. You're looking for a question where the solution is in whole numbers. Terrible example of a Diophantine equation. So we're gonna actually deal with a nice simple kind, the linear Diophantine equations. And in fact, let's do them with just 2 variables, as they do in the book. They're things that look like this. You're given a couple of numbers. We call them A and B in the book. What we want to do is consider the solutions of things that look like a multiple of A plus a multiple of B equals to a third number. Oh, sorry. I guess I just have to add that third number on the end. So we have three integers. Consider solutions of ax plus by equals c, where x and y also need to be integers. So is it clear to everybody that's a linear equation? You should think about, well, if it's a linear equation, it ought to represent the equation of a line. And you can put it into y equals mx plus b form pretty quickly. So first subtract ax from both sides, negative ax plus c. And then divide through by b. Y is equal to negative a over b x plus c over b. You see, that would be the m, that would be the b, the Monte and Bessay in the usual form for the equation of a line. So yeah, that is the equation of a line, ax plus by equals c. It's just not solved for y. It's linear, fine, but there's some weirdness about this setup. Sometimes this will have solutions. In fact, when it has solutions, it'll have infinitely many solutions. It's easy to see. But other times it just won't. You won't be able to find values for x and y that make this linear combination of a and b equal to c. So that's the big question. When does this have solutions? And when are there no solutions? And in the text, they divide the questions of when this kind of equation has a solution and when it doesn't into 4 separate categories. So let's discuss them. Well, actually, maybe before we go discussing them, let me give you an example of this stuff. This is smart to do. Suppose a is equal to 4. B is equal to 10, and C is equal to 6. So I'm looking for x times 4 plus y times 10 equals 6. And I want to try to solve this instead of being smart about it, I just want to solve it in a kind of a brute force way. So let me show you this brute force way. What I'm going to do is imagine the xy plane. And this is the usual xy plane, right? X and y are the axes, and we want those variables to be the x and y, but these guys are only integers, right? So it's not the real number of values versus the real number of values. There's only certain points we're interested in. It's what's known as the integer lattice. Now, I don't want to draw this just in the first quadrant, so I'm also going to back up and have some here in quadrant 2. And maybe some in quadrant 3, I suppose? Or is that 4? I never remember which way these quadrants get numbered. And why am I writing this grid in here? Well, what I want us to do at each point here is we'll label it with 4 times x plus 10 times y. In other words, that's going to be 14, because it's 1 times 4 plus 1 times 10, 14. Oh, actually, the x-axis is easy to label, because then y is 0 on here. So if y is 0, that's gone. Oh, we're just looking at x times 4, so that would be 4, 8, 12, etc. Can you guys tell me what goes at the origin? What number do you have if x and y are both 0? Okay, that wasn't a hard question. In fact, you maybe see the pattern on the x-axis. Moving to the right is adding 4. So moving to the left would be subtracting 4. How much do we change things if we move up on this diagram or down? You know? Yeah, so if we go from the origin up to y equals 1, we get to 10. X would be 0, y would be 1, you get 10. So moving vertically is adding 10. See how 4 turned into 14, 8 will turn into 18, 12 would be 22, there's 32, this would be 28, 24, 20. Okay? So I've actually filled out quite a lot about quadrant 1. The problem is that I'm not going to find 6 in quadrant 1, am I? These are numbers, the only thing smaller than 6 is this 4, and everything else is bigger than that as you head up into quadrant 1. But maybe back in this side or back in this side we'll find it. In fact, I think we're there already. Yeah. Moving from -4 up to 1 unit should add 10 to that, and you get 6. There it is. There's your solution. So why is that? Why is that process a good idea to show you? There's actually other spots in this plane where we get the value of 0. I know when x and y are both 0, we certainly get 0. But can you figure out what x and y values other than 0, 0 will cause it to be 0 as the output? Well, if you kind of switch the roles and throw a minus sign in there, that is, if you have 10 times 4 minus 4 times 10, that'll be 0, and that's when x is 10 and y is 4. X is 10 is way out here, y is 4 isn't that high, it's some point like about out here. So that's where another spot where you get 0. And in fact, all the zeros lie along a line. I just missed it, like that. They're not, well, we're only interested in the integer points where you hit zeros. There may be other ones in here, I'm not quite sure. But you see 6 is just sort of a little bit off of that line. And how far you are from this line where the thing is 0 gets you the possible solutions to things like that. It's, let's see, is there another point where 6 is part of our answer? Like at -2 here, no, not easily. Well, anyway, it is possible to actually find infinitely many points like that where the value is 6. In fact, I'll tell you one way to get them. If you've got a spot where the value is 0, like this one, you just need to kind of move in the same relative fashion. That's 1 up and 1 to the left. 1 up and just off your screen, there'd be a point here where the x-coordinate, or the value of this linear combination would be 6 again. I guess I can tell you what that would be. The x-coordinate goes down by 1, so it's 9 times 4, and the y-coordinate goes up by 1. I think I'm doing something wrong there. The x-coordinate is -10. Not positive 10, that's my problem. -10, and one more to the left, that's -11. Okay? And the y-coordinate is positive. Here it was +4. I want it to be one higher than that, so it's +5. Did I get this right? Yeah, that's -44 plus 50, which is indeed 6. So there's a spot just over here in the same relation to this point as the one labeled 6 is to the origin. And so that helps you to see that, yeah, usually if you get a solution at all, you'll get lots of solutions. Well, why did we get a solution here? And in other scenarios, I'm claiming at least that we won't have solutions. I Think about what happens if these two numbers, like 4 and 10, have a GCD, have a greatest common divisor, have a common divisor at all. Notice what's the GCD of 4 and 10? It's 2. So 2 divides 10, 2 divides 4, that means 2 divides this linear combination, and this all worked because 6 is even. That's really what happened. If I had picked 5 right there, we wouldn't have got any answers. You're never going to get an odd number out of something that looks like a multiple of 4 plus a multiple of 10. All right, so let's talk about this this statement of the theorem here. This is theorem 3.1.2. I guess I should erase what I've got here and start fresh, and we'll actually state the theorem and the 4 cases we look at in order to prove it. All right, so again, we have the setup is 3 integers. This time I'm remembering all 3 of them from the get-go, so I can write it as one group. We want to consider solutions, integer solutions to ax plus by equals c. My brain was getting ahead of myself. I was about to write A on the next thing, so I wrote an A in the word too. Crazy. Ax plus by equals c, where x and y are in the integers. Okay, fine. We are going to assume, assume these things are non-zero. Assume A, B, and C are non-zero. Let's handle both cases. If A is not equal to 0 and B is not equal to 0, yeah. Let D be their GCD. That is, I'm dealing with the case where they're both not equal to 0. If they are both equal to 0, we'll let D be 0. But I'm trying to read Dr. Chrisman's writing here and see what his meaning was. He says this: we will consider cases by ease of generating solutions. I think I know what he means, but it's phrased oddly. So we're going to look at cases, that's fine, and those cases are going to let us figure out the solutions. Again, I'm sorry, I think we want to deal with this slightly differently than he's laid it out. If A and B are both 0, we want D to be 0. And in the other situations, or at least one of them is non-zero. Okay, so here's the fix. Turn that into OR. If A is non-zero or B is non-zero, we'll let D be the GCD. Do just take a minute to notice, what if one of them is 0 but the other isn't? Well, the GCD of 0 and another number is just whatever that other number is. So there still is a GCD when one but not the other is 0. When they're both equal to 0, that's when we need to use D equals 0. Okay, so what's the deal? The first case is actually, seems unmotivated, but it's the simplest one to deal with, so it's kind of like, get this bad thing out of the way. If C here is not a multiple of D, you're toast. You're never going to get a solution. Why? Because D divides A, D divides B, it'll divide this, and if it doesn't divide C, it's just not going to happen. So presumably the other cases are going to be dealing with when there is solutions, or should I say there are solutions. So here's what K is. One or the other, excuse me, I just said that wrong. Here's what the second case is. When either one, when one of A or B is 0, but not both, just one of them is 0, and the non-zero one divides C, then we'll get infinitely many solutions. And what I'm going to do, slightly different from in the book's approach here, is use a without loss of generality comment. One of these two numbers is not 0. If it's fine to just sort of change their names if you need to. So suppose there's a symmetry to this, right? I mean, X and Y are both treated in the same fashion in this thing. So if I interchanged A and B and I interchanged X and Y, we would get the same equation, yeah? So we'll say, without loss of generality, let's make B be 0. Sorry, ended that. So if one of A and B is non-zero, and there's an extra provision in this case that the other one divides D. No, not true. The other one divides C. Excuse me. All right, I read it wrong. So what's the other one? If B is 0, if A divides C, then you're going to have solutions. Infinitely many. Now, in the text, he makes a comment that they're sort of easy to find. So let's deal with that case just a second, and then we'll carry. There's 4 cases total, so we've got 2 more to go through. Fortunately, the second 2 are really, well, the last 2 rather are really quite easy, and they're related to one another. So that's going to be fine. Okay. This is the one I want to deal with. B is 0, A divides C. Can we figure out what the solutions are? I didn't write it into the first one, but I spoke an argument as to why this is correct. And so what I'm trying to do now is justify what's happening in the second case. So what we have is the equation AX plus BY equals C. With B being 0, that term is gone, so it just becomes AX equals C. And we know that A divides C. So A goes evenly into C. That is, you can sort of do the division here and say X is equal to C over A. And I know that this part is an integer. Why? Because we were given, in the case we're dealing with, that A divides C. All right. So we found a solution, but gosh, that seems like we found a unique solution, didn't we? I just got one value for x. What am I supposed to do? Well, that comes into this thing that I crossed out. I crossed it out because b was 0. So y could be, didn't really enter into anything. But that's actually why we get more than one solution. If I have x is equal to c over a and y is anything at all, I still have a solution. So what does that say to us? What does this geometrically say to you if you're in this scenario? If we're in the xy plane with that integer lattice again, c over a is some point on the x-axis. You might think, okay, x is equal to c over a, but it's also c over a with a y-coordinate of 1 and c over a with a y-coordinate of 2. There's all these points that would be solutions. In other words, this case we're dealing with is when the line that includes the solutions is vertical. And my using a without loss of generality thing maybe feels unfair now, but I'll tell you, if you had A being the thing that's 0 and the other one none, then you'd get a horizontal line where all the solutions live. So vertical and horizontal lines are what this second case is about. Well, that means the last two cases must be about, we had a situation where there's no solutions, situation where there's vertical and or horizontal lines full of solutions. What's the other option? The lines are at some angle. They have some slope. And that's what case 3 and 4 deal with. Okay, so 3 is when both a and b are non-zero, and c is actually equal to the GCD. Because d was the GCD of a and b, remember. Well, we have a way to deal with that situation. Why? Because of Bezout's identity, or the Bezout identity, which says the GCD can always be expressed as a linear combination of the two numbers. I mean, it literally says what we've got right here, that d can be written as ax plus by. But if c is equal to d, the Bezout identity immediately gets us that. So let's just see this Bezout identity thing in action for a second. Let's do an example of that with some things that have a reasonable GCD. What's a reasonable GCD? How about 3? 3 is a reasonable GCD, and I need to pick an A and a B so that they have 3 as their greatest common divisor. So how about A is 9 and B is 21? Okay. Just as a quick example. Let's roll through the Euclidean algorithm to find the GCD of these things. Darn. I always like to have A be the bigger one. So I'm sorry, let's change this. Make 21 be A and B be 9. Better? So we want to keep a trace table, A, B, and write A is equal to a quotient times B plus a remainder. Of course, we're going to start with 21 and 9, and remember how you end the Euclidean algorithm when the remainder comes out 0. So 21 is, what's 2 times 9? Plus 3. 18 plus 3 is 21. Cool. The next step has us drop 9 over to here, and the 3 comes from where the 9 was. And that's great because we're already done. 9 is equal to 3 times 3 plus 0. So there's your GCD. Now let's see how that works in producing the Bezout identity. What you want to do is basically solve this equation for the GCD. That 3, right? Actually, I misspoke. It is sort of that 3, but it's not that version of it. It's actually this 3 that we want to look at. That 3, the remainder in the next to last step, is what you're going to be able to solve for. Because 3 is going to be equal to 21 minus 2 times 9. Do you see that as being something times 21 plus something else times 9? That's our x and our y. Well, this one was too easy. We had a one-step application of the Euclidean algorithm, so we got to the answer really quickly. But in general, you have to back your way up from the next to last step all the way to the first step, and finally you'll have the GCD written in terms of linear combinations of the original inputs A and B. Well, let's live with it. We've got an exciting, nice spot here. So x is equal to 1, y is equal to minus 2. That's a point in the plane where if I form the x times 21, y times 9 combinations on the points, this point is going to have a 3 on it. You might not believe me, but let's try it. We're going to be 1 unit out in the x direction is 21, 2 units would be 42. 1 unit up in the y direction would be 9. 2 units would be 18. Every time we move vertically, we add 9. So 21 and 9 gets me to 30 right here. 39 right above it. 42 and 9. Well, maybe it's easier to add 21. Yeah, 51. See, it works the same either way. Either from here, add 21, or from here, add 9. In both cases, you get 21. All right, where am I supposed to be getting a value? I want x is 1, y is minus 2. So here's x is 1, go down 2 units. What do we have to do to go down 2 units? We're moving vertically. That means instead of adding 9 to go down, we'll subtract 9. So 21 minus 9, that's 12. 12 minus 9, that's 3. And there are going to be other points that have a 3 on them, but they're actually related to the line where this ax plus by would be equal to 0. But anyway, having located 1 is kind of enough to get all the rest of them. That spot would be 0, right? Yeah, so the line that we're interested in would have these solutions on it is something like that. It actually passes a little closer to there than I drew. But, it's got a pretty steep slope, but its slope happens to be 21 over 9. Well, actually the negative of that. Negative 2 something. Does that look like a minus 2 slope? Just about. All right, so that's case 3. Now there's case 4 to deal with. And fortunately, this last final case to deal with is pretty easy. It's when, C is not equal to the GCD, but it's a multiple of the GCD. Let's put it that way. So, where the GCD divides C, maybe is a better way to say it. They're not equal. So again, we have A not 0, B not 0, and C is equal to some multiple of D, where D, again, is the GCD. So we've got a multiple of GCD of A and B. So what's nice here is we already know that the third case is dealt with, so that there will be solutions to ax plus by equals d. So how are we going to get a solution of ax plus by equals this c? It's a multiple of d. Multiply reality by m. Just, oh gosh, I was kind of sloppy here. I said c was a multiple of d, but I didn't say where m lived. M is an integer, and in particular, it should not be equal to 1. But because if it was 1, or actually I guess minus 1 would be a similar issue. We're really in the previous case. Yeah. So yeah, what you got to do is multiply by m. So you'll have am x plus bm y equals dm. If you've got an equation that's true and you multiply both sides by something, you've got another equation that's true. It's interesting that multiplying by m doesn't really change the slope of this line, because you know the slope of the line is basically the ratio of these coefficients. It's actually the negative of the ratio of the coefficients. So the slope would be a over b with a minus sign. There's m's in both of those too, but those cancel, right? So that's the slope of the line. It's the same as the slope of the line when we just had d. In fact, the slope of the lines for any solution are always the same. It's negative a over b. Well, there's an app in the book, not an app, excuse me, a Sage cell in the book where you can fiddle around with this a little bit. You can try different values for a and b. In particular, see what happens when you set one of them to 0. I didn't understand why he didn't deal with the case where a and b were both 0. Maybe that's easy. If a and b are both 0, any combination of them will still be 0. Unless c is 0, you're hosed. And if c is 0, well then a times, or 0 times something plus 0 times something else equals 0. I think you can use whatever you like in x and y. In other words, 0x plus 0y equals 0. What's the solution set for that? Every single possible pair of integers. That's the entire integer lattice. I guess you didn't really need to deal with that. It's too easy. Okay.